Okay, good morning, guys. Can you please tell me what your questions are? If you have any, good morning. Thanks, Lori. Okay, questions. Which questions you have from the homework? You can either put them on chat as usual or just let me know what they are. Ben, can you hear me? Ben Ipema.
Yeah, I can hear you.
Yeah, I sent you a note yesterday. Did you receive it? I just wonder because I don't know if you get it or not. Did you receive anything? When I graded your quiz 0, I sent a note, and I don't know if you guys received the note or not. Did you get anything? Tell me yes or no. Okay. Okay, Maddie, you got it? Yes, okay, great. So next time, if I want to send any remark, I will do the same way. I just want to make sure that you guys are receiving it. Thanks. Okay, so can we go over 7, 17, and 19? All right. So we're gonna go over 7, 17, and 19. Anything else? All right, let's go. Most of the problems in this section are dealing with the limit comparison test, which is basically that we have a series that we don't know what to do with it. So we would like to compare it to another one that we know its behavior. And the limit comparison test tells me how to compare it. So what's the mathematical procedure to do that? So we're gonna start looking at number 17. Okay, and please let me know if everything is clear or not, so we can play with it with the camera a little bit. So number 7. So number 7 is the following. We have the following series: sigma 9 to the n over 3 plus 10 to the n, and n equal 1 to infinity. And the question is, does the series converge or diverge? It's really, if we look at it, we have no idea really what it is. So we're gonna stare at its general term. It means when we're adding the terms, something plus, etc., we're gonna look at how does this general term looks like. So we're gonna look at A sub n. And A sub n is 9 to the n over 3 plus 10 to the power n. And we're going to ask ourselves the following question. When n is very large, and that's crucial, when n is very large, the values that an are taking are close to what? That's really how we're going to handle those problems. All right, so let's see. Can you guys give me an answer? I'm having good answers. Anybody else? Can you blur a little? Can you write a little bit bigger, please? It's kind of blurry. Okay. I'm trying to use the focus of the camera. See if it does help any. Is it still blurry? Okay, I will try bigger, definitely. So now, the top 9 to the n. Oh, 9 to the n. It's 9 to the n. There is nothing I can do about it. What about the denominator? 3 plus 10 to the n. When n is very large, 10 to the n is huge. So compared to 3, I can basically drop 3. So the denominator is actually 10 to the power 9. So that's how we're going to really think about that. So now this is nothing more than 9 over 10 to the power n. So when n is large, the terms, those an, they almost have the same value, almost, not equal, as 9/10 to the power n. Very much so. So this is going to be my choice of Bn. That's how we choose Bn. We ask ourselves for n is large, you know, my series, the term of my series look like something like what? And we try to compare it to something that we actually understand their behavior. So now let's look at sigma Bn. What is sigma Bn? Sigma Bn is sigma 9/10 to the power n. Now here's your question. What type of series is sigma Bn? Do we know the behavior of this new series? Have we seen anything like that? Absolutely, that's a geometric, yeah, exactly. That's a geometric series. And we know all about geometric series. One of the two series we understand their behavior are the geometric and the P series. So whenever we want to compare the terms of our series to something, we have to compare them to geometric or P series, because these are the ones we know their behavior. That's about the only thing we know. So this is sigma Bn. This one converges because that's, no, sorry, I skipped this step. I skipped this step. What did I skip? What did I skip? So I'm going to scratch this for now. What did I skip? I skipped the following fact, checking for L. Absolutely, I have to check for L. So sorry, I'm going to skip that. And I'm going to take L. I'm going to take the limit as n tends to infinity of an over Bn. Now I made my choice. I want to make sure that my choice is actually correct. It means, is an and Bn kind of close to each other or not? So I want to make sure that my limit is not 0 and not infinity. So let us compute this limit. So that's the limit as n tends to infinity of my an is 9^n over 3 plus 10^n. What's my Bn? My Bn is 9^n over 10^n. I want to compute this limit and make sure that actually they are comparable. It's not 0. So let's do that. Okay, that's my limit right here. I'm gonna compute it. So that's the limit as n tends to infinity of 9^n over 3 plus 10^n times 10^n over 9. Okay, so this is equal to what? 9^n, they cancel out, exactly. And then this would leave me with the limit as n tends to infinity of 10^n over 3 plus 10^n. So what's going to be the ratio in this case? Can we see the ratio? I mean, we can intuitively, when n is large, the denominator is almost 10^n. So I really basically have 10^n over 10^n. This is equal to 1. So I'm really doing a very good comparison. So this limit is not 0 and is not infinity. So now I can use the limit comparison test. So now by the limit comparison test, what do we have? Sigma Bn, which is sigma 9/10 to the power n. This one converges. That's a geometric where the ratio is 9/10. So my ratio is less than 1. So that's a geometric with ratio less than 1. The ratio is less than 1. That's why it converges. So by the limit comparison, my original series, sigma an, also converge. Okay? Questions before I go on? All right. All right, so now let's look at the other problems that you guys asked. So it's number 17. So let's look at number 17. Okay, so what it is? 17 is sigma 1 over the square root of n squared plus 1 from 1 to infinity. And again, this is not a p-series, it's not a geometric, but you want to compare it to one of those. So again, I take its general term. That's usually my first step. And I ask myself, when n is large, and that's crucial, not for every value of n, only when n is large. This behaves like what? All right? Who would like to tell me? I want somebody to answer. 1 over n, I'm getting one answer. Anybody else? So how are we gonna think about it? Somebody unmute themselves and tell me, how do you think about it? I don't mind hearing your voices.
I tried to think about it as 1 over n to the 1/2.
Yeah, I repeat. I did not hear you very well.
Oh, I like to think about it as 1 over n to the 2 over 2, because you've got a square root over the squared, because you can drop away the 1.
You drop the 1, exactly. So now the way we're going to think about it, when n is large, think about n large, we can drop the 1. So that's become 1 over square root of n squared. Now, this is nothing more than 1 over n, and this is my bn. So that's how we are doing it. When n is large, those two terms are very close to one another. So if adding those terms, we get to somewhere. Adding those, we get to somewhere. If adding those, it will diverge. Adding those will diverge. So basically, we're adding at the end. But because those are very comparable, then sigma, the sum of those is not equal, but we can compare them to each other. So if those will diverge, those one will diverge. But since just talking doesn't do the work, we have to do it in a mathematically correct way. And the mathematically correct way is to take the limit as n tends to infinity of the ratio and make sure that actually I'm choosing the n correctly. I'm not over choosing. I'm not choosing something wrong. So again, back to our limit ideas. So we're going to compute what happened when n goes to infinity of my an, which is 1 over the square root of n squared plus 1. My an is 1 over n. So this is going to give me the following. The limit as n tends to infinity of n, you do the math easily, sorry, n over the square root of n squared plus 1. So what's the limit of that? Now, we did something fairly similar when we worked with sequences before. And to compute this limit, if you guys remember, what am I going to do to compute the limit? I want an answer without somebody unmute and tell me. How do you compute this limit?
Can you just put everything under the square root?
We're going to put everything under the square root because now n, because I've done this before, this is the square root of n squared. And this will save the day for us because this is going to give me this piece. Very good. Now, what's the limit of that piece? N squared over n squared plus 1. When n is large, you can divide by n squared numerator and denominator. You're going to get a 1. Now, we don't always have to get a 1, but we're making a good choices, we get 1. So now the limit is 1, so the limit of comparison test will apply. So now by the limit comparison test, my limit, crucial, I have to make sure my limit is not infinity. And my limit is not 0. So by the limit comparison, so we can apply. So the limit comparison test can be applied. That's what's happening. I can apply the limit comparison test. Now, sigma Bn, which is sigma 1 over n, this one diverges. Because why it diverges? Quickly. I want answers. That's the harmonic series, or that's a P series, where P is equal to 1. So we are always going to compare to things we know. So sigma Bn diverges because it's P series, hence my original series, sigma 1 over the square root of n squared plus 1 will also diverge. All right. Yeah, I look at the other last problem you guys asked, 7, 17, and 19. Okay. Questions before I move on? Okay. So let's look at 19. Okay. Again, it's the same type problem. Sigma n plus 1 over n to the power 3 plus n from 1 to infinity. All right. Again, we're going to use the limit comparison. And that's exactly what we are being doing. Enlarge. Enlarge. So this is going to behave like what? All right, the numerator. We do it numerator, then denominator. When n is large, the numerator behaves like what? Quickly. N, that's the numerator. Denominator, I do it piece by piece. N to the power 3 plus n. When n is very large.
N cubed.
N cubed. The term with the highest power really is going to take over. That's n cubed. So now this is going to give me 1 over n squared. And this is the Bn I'm going to go after. Now I'm going to compute the ratio as n tends to infinity of an over Bn. I want to always make sure that I'm choosing the right series. Because if I goof here, I don't choose the right series, when I'm computing the limit, I may not have a number which is different from 0, different from infinity. It means I may have 0 or infinity, then there is no conclusion. That's why we have to make sure that what we're picking is the correct choice, one of the correct choices. So now an over Bn, if we do it, it's going to give me n plus 1 over n to the power 3 plus n times n squared plus 1. So this will give me the limit of n to the power 3 plus n, so I multiply across, over, sorry, plus n squared, multiply across, over n to the power 3 plus n. All right? And what's this limit here? Now we've done this gazillion times. You can divide by n to the power 3, numerator, denominator. You're gonna get 1 over n here, and you're gonna get 1 over n squared here. Doing this, as n goes to infinity, this goes to 0, this goes to 0, equal to 1. So my choice will work. And now, so the limit comparison test, limit comparison test applies. So I can really actually use it because my limit is not 0 and it's not infinity. So now what does my limit comparison test tells me? Sigma Bn, this series converges because it's a P series where P is equal to 2. Hence my original series, Sigma An, will also converge. So let me sum this up into words. Now, Sigma Bn, which is sigma 1 over n squared, converges because it's a P series. We should always give a reason why it converges, where P is equal to 2. Hence, my original one, which is n plus 1 over n to the 3 plus n, also converges. And of the problem. Any questions before I ask you some myself? Could we look at number 14? Could we look at number 14? Yes, we can. All right, let's look at number 14. Very good. That's my series. And it's 1 over the cubic root. So, yep, 3n to the power 4 plus 1. Okay? All right. Again, the same idea. Enlarge. That's An. We're going to study its behavior when n is large. All right. I give you 2 minutes for every one of you to tell me what would you like to compare it with. And then you either, as usual, put it on your chat or unmute yourself and tell me. Okay. All right, I'm having one answer. I want the others. Okay, I have 2 correct answers. So let us really sum them up. This will behave like what? 1 is 1, the denominator. 3 and 4 plus 1. Basically, you can drop the 1 and you can put 3n to the power 4, 3, the cubic root of that. Okay, which is equal to, I know that the 3 is bothering us, but the 3 really should not actually bother us. So this is basically 1 over 3 to the power a third times n to the power 4/3. Okay. Now I know what Christian and Connor wrote. They are absolutely correct. But actually, I'm going to keep 3 to the power 1/3. That's not really a big deal times that. But we can do it both ways. It doesn't really matter. So I'm going to pick this to be my Bn. Now, let me ask you the following questions before I proceed and finish this. A very intuitive questions, and then I'll come back to that problem. Let us say I take a sequence, a series, and then I'll come back to this problem. Question, suppose I give you a series, sigma An, and I tell you that this series converges. So what is sigma An? A1 plus A2 plus A3 plus, and this converge. I'm giving you that. And suppose now I take another series by multiplying each term by a constant. Suppose I take the following series, 2 times an. It means 2a1 plus 2a2 plus 2a3 plus dot dot. So it's the same, but I multiply every term by a constant. Will the new series converges? What do you think? So the first one converges. I multiply each term by 2. Will the new one also converge? Okay, Philip is telling me yes. Anybody agree with him? Absolutely, it will converge. If you think in terms of partial sums, the partial sums are very much related. So for the first series, think about the partial sums. The first series, Sn is a1. I always think about those problems as partial sums, plus a2, plus a3, plus etc. The second one, I'm going to call the partial sum Tn, is 2a1 plus 2a2 plus 2a3, etc. plus 2an. So the partial sums for the second series is nothing more than twice the partial sums of the first series. So if Sn will converge to S, the second one will converge to twice S. So multiplying a series by a constant, and that's crucial, will not affect the behavior. If the first converge, the second will. If the first diverge, the second will diverge. Simple fact, but we definitely should be aware of it. So now why I am talking about that fact. So suppose a student did not give me this as Bn, which is absolutely correct. But they say, this is my Bn. That's really actually enough, because if sigma 1 over n to the power 4/3 diverge, multiplying by a constant, it will diverge as well. So you really have two choices for the Bn. Both of them are correct, without this constant and with this constant. All right. Now being said, let us finish this problem. So this is my 8Bn. And then I'm going to compute the ratio and then proceed. So I always compute the ratio. I always want to make sure I'm not goofing in my choice. So let us take my L. That's the limit as n tends to infinity of a n over b to the n. That's the limit as n tends to infinity of. Very good. So what is an? An is 1 over the cubic root of 3n to the 4 plus 1 times, okay, I had 3 to the power a third, which is not a big deal, times n to the power 4/3. All right, so what's the limit of that? Now, of course, n to the power 4/3 is nothing more than the cubic root of n to the 4. So basically, I'm going to have 3 to the 3rd times the cubic root of n4, because n to the 4/3 is the cubic root of n4, divided by 3 and 4 plus 1. Now we know that this one, the inside, is going to go to 1/3. I multiply it by this, I get 1. Okay. Now let me make a small comment in the following. No, I'll finish and then I'll make comment for the student who picked another series. So now I have to go limit comparison test applies in the scenario. I really want to make sure that I can apply it. I have to check. Now, since the following series, sigma Bn is sigma of, what did we pick it? 1 over cubic root of 3 times n to the power 4/3. Now, cubic root of 3 is a constant. I really don't have to worry about. But what do we know? Does sigma bn converge or diverge? Converge or diverge? Converge. Okay, is she right? Converges because it's a p series with p equal 4/3. Constant do not bother us. So we can almost think of them as p series with p equals 4/3. So my original series also converges. Okay. All right. Anything else? All right. So that's how the limit comparison test works. It's not perfect, but it's a very, very good test. Yeah, it converges, absolutely converges. And next time on Monday, we're going to start other tests. All the tests we saw so far, whether it's the integral test or the limit comparison test, works for series with positive terms. On Monday, we're going to start including series with negative terms, which are actually usually harder. So we're going to take a very specific case of them. All right. Any other questions? Okay, so we're gonna go start our quiz. You guys go to Blackboard, all of you. And like you did yesterday for quiz 0, I have quiz, I think 7. Go to content area, click on quizzes. So content area, click quizzes. When you do that, is everybody on board? Everybody on board, please say yes. I want to know if you are on board. And then you click like you did yesterday. Quiz 7. Right? Open it and get going. I gave you enough time to take the quiz. You guys really have enough time to take the quiz. I think you should give it back to me. You should hand it at 12:30. And now, one more comment before I let you go, that the time on Blackboard is West Lafayette time. The time on Blackboard is West Lafayette time, which are an hour ahead of us. So even if your Blackboard say 1:30, it means it's 12:30 our time. So, and of course, I'm working with our time, but that's Blackboard, I can't change it. So Blackboard is West Lafayette time, not our time. So the quiz should be on Blackboard for me at 12:30. Please write very clearly and neatly because I have to read this. Okay? Good luck. Bye, guys, and enjoy your weekend. Allô? Allô? Allô?